So in order to calculate Cauchy constant, we need the following things. They are light sources, spectrometer and glass prism. So you can see the spectrometer in the figure, which will be described later on the virtual lab. So by using the spectrometer, we can calculate angle of prism, angle of minimum deviation for the particular color of the light. So we can calculate the refractive index. Then we can use Cauchy relation, and we can plug the refractive index calculated from here, and then we can just plug here the wavelength for which the refractive index is calculated. Then by plotting the graph, we can just find out the value of the Cauchy constant A and B. A is given by the y-intercept, and the value of B is given by the slope of this curve. So now we are here in the simulation page. So in order to so now we are here in the simulation page. So we have to maximize it so we can see it more clearly. So first step in the simulation is to focus on the object. This is the telescope lens, so we have to focus it on this object. So just focus it by increasing the focus. You can check it out. So it's now ready. So let's get started. Wait for a little bit. So we can see the complete spectrometer here. Here you can see the light source, collimator, and this is the telescope lens where you can see the light spectrum. So this is the Vernier scale, and this is the Vernier scale 2 here, mounted on the rotating Vernier table. So first of all, we have to switch on the light by pressing here. So light is switched on. So you can see here, you can rotate this to see the light spectrum. So you can focus it, make it sharp. You can check out. You can control the slit width. Okay, now I'm going to just click here. You can also click here to rotate this one. This is the telescope, so just make it as a center. Just you can press arrow keys, left and right arrows, to make it like this. Okay, so our spectrometer is ready. So let us find the least count of this spectrometer first. So we can see that this this telescope, as we rotate, we can see it can travel around 360 degree. You can see it. Okay, there is 0 degree, and there is 350 degree, and there is up to 0 is 360 degree. So what we can say is that this line is equivalent to 1 degree. So it is further divided so that it's a single line. This one is actually 0.5 degree. So if we divide 0.5 degree by this 30 divisions, then we will get around 1 minute. So 1 minute is actually the least count for this spectrometer, and which is nearly equal to 0.02 degree. So we can also see it. So we can also see it here. The least count is equal to value of 1 main scale division by total number of Vernier scale divisions. So we said this is 0.5 degree divided by 30 is equal to 1 minute. So in order to find the angle of the prism, we have to place the prism on the Vernier rotating table by placing place prism. So prism is here, the light is coming from here, it will bounce off and reflected from this prism faces, two of these faces. And what we can do is we can just place our cross wire of this telescope by rotating it, and then we can record out the position of the light spectra. So let's go, just rotate it, rotate it, rotate it, rotate it. Okay, go on, go on, go on. Still not coming, still not coming. Okay, okay, it's coming. So just go to the telescope fine adjustment and press left button. Okay, it will just come and it will just go here. Okay, then our crosswire is at the center of the spectrum. So what we can do is we can note out the reading. So in order to note out the reading, this is the 290, so it's coincide with 0. So our main scale reading is 290, and 10 is perfectly aligned with another scale, that is main scale and vernier scale are perfectly aligned here, this line. So we can take 10 as the vernier scale. So our reading is 290 plus 10, sorry, 290 plus, yes, 10 into 1 minute will be the vernier 1 reading. Similarly for vernier 2, so you can also press Ctrl and middle mouse scroll up button. So you can check out, you can just go here, and this is 110, and base coincide is, let's say, 19. So this is 110 plus 19 into 1 minute is the vernier 2 reading for the phase 1. So now we have the vernier reading V1 and V2 for the phase 1. Similarly, rotate the telescope around, rotate, rotate, okay, rotate, rotate, okay, the spectrum is coming, going, okay, it's coming, and just go to the fine angle and just press left button, okay, then go on, go on, go on, go on, go on, go on, okay, it's completely now. So you can notice this is the 50, and base coincide is maybe what is this, this is 10, so 50 plus 10 into 1 minute. Similarly you can note the V2. So we have a vernier 1 and vernier 2 scale for the phase 2. So overall we have phase 1 vernier 1 and vernier 2, as well as phase 2 vernier and vernier 2 reading. Now let's move to our table. Yes, by subtracting those two, we can find out the difference, and dividing it by 2 we get the angle of prism. Similarly we can find here also. So the angle of prism was found to be 59.95 degree. The angle of minimum deviation, we have to place the prism first and rotate the vernier table so that the collimator and the base of prism will be almost parallel. Sorry, I mean vernier table first. Okay, rotate vernier table first. Okay, almost parallel these two are. So now we will be observing the spectrum. Since the light is coming from this phase, it will just disperse around this base, so we have to observe the spectra there. So let's go. Okay, spectra is there. Just go to this telescope and just adjust it left and right. You can see the whole spectra here. Okay, now you have to find out the position for the minimum deviation. So for that you have to again rotate the vernier table slowly. So you have to find the position where the waves will be stationary and will return to the opposite direction. Okay, let's find out. Okay, okay, let's go a little bit further. Okay, it is a little bit harder, so we have to capture it like this. So this finding is a little bit challenging. Go to this one and send it. Okay, it's going in front. Okay, it's going. Okay, it's reading back. Okay, so again go here, go a little bit front. You can just go a little bit front. Okay, we are here now. What we can do is, oh shit, okay, just go to the press. I'm pressing okay, I'm going right. Okay, I'm pressing right button and it's going toward the left. The fringe is moving. Okay, moving to the left, 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 and now it's returning back. Means I have to a little bit go again further. So I have to pull it back here. Then again I have to go to vernier. So again I have to move it left, left, left. It's moving left, 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 left. Okay, this is the point. So go to the telescope. Now you can just go around this point. So now go to Vernier again. You can see I'm moving, pressing the right button, and the fringes are moving to opposite direction. See, if I go to the left, 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 now there is stationary here, and they are moving to the right. So let's focus to that point little bit more, you will see it. So go to Vernier table. Now you can see here. Okay, if I go to left, left, pressing left, and it's going what is coming back. So let's see, again I'm pressing the right, right is going to the left, left, going left, left, it's become stationary, going left, now it's changed again, it's coming back. So that is the point of angle of minimum deviation. So let's adjust it here. Okay, this is the point of the minimum deviation. Okay, it is the point where the fringes will just start to travel in the opposite direction, and the point where it just starts, that's the stationary point. That point we have to record the Vernier 1 and Vernier 2. So for the red light, just focus the telescope now at this point, go to the red light. Okay, this is okay, this stationary point. Okay, go to the red light and record Vernier 1 and Vernier 2 for the red light. Okay, and then again go to the yellow light, record Vernier and Vernier 2. Similarly for green light, for blue light, and for violet light, you can record the V1 and V2 for the minimum deviation. So after that, you have to remove the prism like this, and then you have to take the direct reading. For direct reading, you have to go to the telescope like this. Okay, you can just set it to 0. So, and you can note the Vernier 1 and Vernier 2 scale for the direct reading. So the data will look like, so for the red light we have Vernier 1 and Vernier 2 for the minimum deviation, for yellow light, for green light, and for blue light, and for violet light. And we have direct reading for the telescope are this and this as B1 and B2. So if we subtract this direct reading from the minimum deviation, we'll get the difference, that is the angle of minimum deviation. Okay, so we have calculated the angle of minimum deviation for different colors as shown. So we can take the average between these two and find the angle of minimum deviation for the particular color. Okay, so we have already calculated angle of prism. Now we have calculated angle of minimum deviation. By using this and this, we can calculate the refractive index for the particular color line. So we have calculated for red line, yellow line, green line, blue line, and violet line the refractive index also. So we have calculated the refractive index for the particular color of light, and in the simulator page we are provided with the wavelengths for yellow, green, blue, and violet too. So we'll be using only refractive index for those only, excluding the red color. So we have wavelength in nanometers, and this is given from the table in the simulation page, and this is the inverse square of the wavelength. Okay, so we have to plot a graph between a refractive index and inverse square of the wavelength, this data. So I am doing here the base fit for the data. So this is a line, this is the base fit line, which is equal to y equal to mx plus c, and what we found is that the intercept was found to be 1.41526, and the slope was found to be 4.2324 into 10 to the power minus 15. So here what we can say, that the a, that is the Cauchy constant a, is actually the intercept part, and the slope gives the Cauchy constant b. So we have calculated the value of A and B from the graph. Okay, so what we can say that by using the simulation we have successfully calculated the value of Cauchy's constant A and B. So we can say that the virtual lab is also very reliable in case we couldn't perform an experiment in the lab. So I would like to thank Dean Office, Head OPN Sir from Central Department of Physics, my friends, my expected teachers for helping out to perform this virtual lab simulation, and I hope everyone will be more interested in doing it and submitting it. So thank you for watching. I will be very much happy if someone will just point out the any errors, mistakes, and always hopeful to hear from my friends. Thank you.